You don't have to ask. You just go, okay. Yeah. Okay. So the binomial theorem, what you're going to see is in some ways you might look at it like, what's it got to do with what we've been doing before? But mostly what we've been doing before is about sequences of numbers. And the binomial theorem tells us how to generate a certain sequence of numbers. They're not arithmetic. They're not geometric. They're their own thing. And they are somewhat useful. Right. So a binomial expansion is when you take a binomial, which means two terms, right, and you raise it to a power. So example, the general binomial is x plus y. Okay, there's your two terms. And you're raising it to a power. You can see what you get for up to the fifth power right there, right? When you raise anything to the 0, you get 1. You raise it to the first power, you just get x plus y. Now, when you say x plus y squared, that's a FOIL, right? You would have to do x plus y times x plus y, right? And this is fairly familiar, right? X squared plus 2x xy plus y squared. But when you start to get up higher now, like x plus y to the third, then you would have to take this x plus y squared and multiply it by x plus y, right? And to get x plus y to the fourth, you would have to take the x plus y to the third and multiply it times x plus y, and so on and so on. And you could see that in every case, I mean, look at the pattern that there is here. First, let's go all the way down to the bottom line here. The first term is all x, right? X to the fifth. It's what you get if you have x plus y multiplied 5 times. The first term would be x times x times x times x times x, x to the fifth, right? The next term, in order now, will have x to the fourth, 1 less power of x. And now it has y to the first. The next term is x to the third, so it's 1 less power of x, y squared, 1 more power of y. And you just notice that the pattern continues, right? The next term is 1 less power of x and 1 more power of y. The next one is x to the first, y to the fourth, right? And if I go down 1, right, I've got x 1 time. In the next term, that means there is no x. And there's 1 more y, so it's y to the fifth. So that's always the pattern. When you do the binomial expansion, it's always you're going to start with the first term is all x, and then the powers of x go down, and the powers of the second term in the binomial, they go up. Now, what's unexplained by that are the coefficients of those terms. And those, I mean, we know where they come from. I mean, like this 2xy, if I do the x plus y times x plus y, we get x squared plus xy plus xy plus y squared, right? The reason that we got 2xy is because we combine like terms, and that's what you get, right? Well, it's the same thing here. As we keep multiplying by another xy, we keep generating, more like terms that can be combined. And these coefficients are just the result of combining like terms. So what the binomial theorem is going to do for us is just tell us what those numbers are. So we're not going to multiply these things out longhand so that we can combine all the like terms and know what those numbers are. The binomial theorem will generate that sequence of numbers for us. I guess that's why it's in this chapter about sequences. It's a different pattern. Okay. First, I'll say the complicated way. Right? The binomial theorem tells us a formula for a binomial expansion, x plus y to the nth. Okay, and you could see that the first term is all x, right? The last term is all y, and you could see the second term in is x to the n minus 1. It's 1 less than the first term was. And now it's got the y to the first. the second to the last term has got the x to the first and y to the n minus 1, right? And that would be the pattern. The x's are going down, the y's are going up. And again, we would just have to figure out what are these coefficients that we're supposed to use. I can write down the pattern right away. I could tell you, the right powers of the variables. But now I need to know what are the coefficients that I'm going to generate by combining like terms. And that formula is right here. Okay. And you should have seen that before. Does anybody recognize the NCR? We did two things like that at the end of Algebra 2, or somewhere in Algebra 2. NCR and NPR. Conjugate? No. Starts with a C. That's why it's a C. Combination? Permutation. Yeah, permutation and combinations. Okay, well that is how you get this. You do the combination thing that you did in Algebra 2. That's how you generate the coefficients for the binomial theorem. It's a combination. So, so this is just the general term. Now notice that NCR, right? The N is, when we use this for combinations, it works something like this. Okay, there's 20 of us in here. How many different combinations of 5 people could I get from this group, right? So the N was that first number, and that would have been the 20. The 5 would have been the second number. In this case, because we're raising x plus y to the n power, or whatever power that is, that's the first number. That's the n. And then you can see as the exponent of x goes down, right, and the exponent of y goes up, that in any particular term, the r that you've got, that's the power of y. Those two match. That's how you figure out what you're going to use. Now, this was the formula for a combination, right? You've got NCR, then that's n factorial over n minus r factorial, r factorial. And you should note that they sometimes use a different notation for that. That this, if you use like parentheses like this with n over r, it means the same thing. These two things here are the same. They both mean that. So the book sometimes will ask it like this, and sometimes you're going to ask it like that. But it's the same thing. Okay, let's see. Okay, so again, here's the examples where they're going to do it 4 times. And 2 of them they've written with the NCR notation. The other one they've written with n over r notation. But it works out the same anyways. Right? For the 8C2, right, you've got 8 factorial over 8 minus 2 factorial, which is 6 factorial, and 2 factorial. I think that was probably exactly something that we did as an example or a homework problem in the first section, simplifying factorials. So if you remember, there was like, in their examples, they just showed 8 times 7 times 6 times 5 all the way down to 1. They wrote them all out in terms of all their factors, and they canceled the common factors. And I think I showed you more like this. See if this works. There we go. Come on, do it. Not sure why that doesn't want to erase. Maybe no, that's actually the wrong thing to do. That was like supposed to be my presto magic thing here. And it didn't even work. Okay, we can kind of see what's there anyways. In this case, in order to simplify, they just split off the first 2, 8 times 7 and then they let the 6 factorial take care of the rest. And then in the denominator, because they had a 6 factorial, just cancel the 6 factorial. But there's no reason to write out 6 times 5 times 4 times 3 times 2 times 1. You're going to cancel them anyways. So what's left is 8 times 7 divided by 2 times 1, 28. Right? The 10 over 3 in the other format is still 10 factorial over 10 minus 3 factorial, which was the 7 factorial, 3 factorial. I mean, you can see in all these, the denominator, if you just look at the numbers, adds up to the top. It has to. 6 plus 2 is 8. 7 plus 3 is 10. Right? So in this case, let's see if it'll erase for me. That one worked a little better. Oh, now it's gone. Right? In this one, they just peel off the 10 times 9 times 8 because the 7 factorials will cancel each other. Usually you're going to peel off just enough so that you can cancel the biggest factorial in the denominator. I mean, would it make sense to go, we could go 10 times 9 times 8 times 7 times 6 times 5 times 4 so we can cancel the 3 factorials, but then we'd have a whole lot more work to do. It's easier to like cancel the biggest thing you can on the other side. And what's left is, see how they do that. I'm not sure why that doesn't go better than that. 10 times 9 times 8, and the denominator 3 times 2 times 1, and that can be simplified. I mean, you could do it more easily than that, right? You could divide the 3 goes into 9 3 times, 2 goes into 8 4 times, 3 times 4 is 12, times 10 is 120. Now notice if you're making these terms for the binomial theorem, right, the first term and the last term, right, remember what we said about this NCR. The R there is the power of y. So in the first term, the power of y is 0. So you're going to have an NCR where the R is 0. The last term, it's going to be NCN. So that's what these examples are here, these last two. You know, what do you get if it's 7C0? Well, that would be 7 factorial over 7 factorial times 0 factorial. Clearly, the 7 factorials are just going to cancel each other. And 0 factorial, by definition, is 1. So this whole thing is 1. And the same thing is going to happen with the 8, you know, written in the different format. Right? It'll look like 8 factorial, 8 minus 8 factorial, 8 factorial. The 8 factorials cancel, and 0 factorial is 1. So it's 1. So again, go back to this. In every one of these, what was the coefficient of the first term and the last term? 1. So that's consistent with the binomial theorem and using the combination notation to do that. And this one, enough fun and games there. Right, so notice here, right, the 7C3 and written in the different notation, but this thing is 7C4, written like that, are the same thing, right? If you go back to here, I mean, notice the pattern of the numbers, right? In every case, right? 1 2 1, 1 3 3 1, 1 4 6 4 1. There's a pattern to them, right? They're symmetric, and so in this case, because where am I at? This is 7C3 and 7C4. They would be the exact two middle terms of the binomial expansion. So their coefficients are going to be are equal. Okay. And you could see how that works out. But they're equal. And the same thing would be like this one right here would be the second term in an expansion. This would be the second to the last term in an expansion. They should be equal because it's symmetric. right? 12 and 12. In fact, in the binomial expansion, notice this is like if the n is 12, so you're raising it to the 12th power. And in the binomial theorem, you could see that they had already put n as the coefficient of the second term and the second to the last term, right? And that's what it would be. Okay, so we say all of this so that we can, well, I guess we're not quite there yet. So that's using the combination notation to do this, okay? There's another way to do this, which is probably the way you're going to do it. It's probably not going to be going through and doing many calculations like this to come up with your binomial coefficients. Instead, you're going to be using something that we call Pascal's triangle. And Pascal's triangle is something that you can construct really easily for yourself if you need to find the coefficients for a binomial expansion, right? You always start out the triangle at the top with a 1, basically. And you're down on the second row, you're adding up the numbers that are above it to the left and to the right. So if I add up from this position here, there's nothing over here, and there's a 1 there, so it's a 1. Right? From here, if I'm adding up a 1 and a 0, it's a 1. In the next row down, right, again, on the edges, it's always going to be like this. It'll be 0 plus 1 is 1. Right? That's because the first term has always got a coefficient of 1, and the last term always is the coefficient of 1. But in the middle here, right, now I'm adding up a 1 plus a 1, and I get a 2. Right? In the next line, it's 1, 3, because 1 plus 2 is 3. 3, because 2 plus 1 is 3, 1. Right? The next row, 1, 4, 6, 4, 1. So normally, if you do a binomial expansion and you need some coefficients, go back to this slide right here. If I'm raising something to the second power, you can see right there, how many terms do I need? How many coefficients will I need for all the terms that I'm going to make? 3. There's 3 terms, I need 3 coefficients. All right. For the x plus y to the third, how many terms do I have? 4, right? For the fifth power, how many terms? 1, 2, 3, 4, 5, 6. You always have one more term than the power you're raising that binomial to, which makes sense, right? Because you start with the highest power of x, and then you go all the way down to 1, and then there's 1 extra term. Or you start with a term that doesn't have any y's in it, and then you go from 1 to n. So it's always one more than whatever the n is. So if I'm raising something to the fifth power, I know I need 6 coefficients. So I just start making that Pascal's triangle until I made 6 numbers. Then I'm done. Right. So notice these numbers, 1, 5, 10, 10, 5, 1. Right. I would just start making my triangle until I got down to this row, because there's 6 numbers now, 1, 5, 10, 10, 5, 1, and that's what I put in front of it. I don't really go to calculating 5C0, 5C1, 5C2, 5C3. I don't have to do that, right? I just make my Pascal's triangle, grab the coefficients that I need, done. And usually when you're doing this kind of thing, you're doing the triangle. And you just go to the side and make yourself the triangle. Not that hard. Now, something interesting about this is that if you plotted these, if you made like a dot plot of this, something like, in the first row, I'll put a 1. Let's say I'm doing this row right here. I'd have 1. And in the next, I would have a 7. So 1, 2, 3, 4, 5, 6, 7. Right? And the next, it would go up 21. And the next, it would go up 35. And the next, 35 and 21 and 7 and 1. Then that curve is a bell curve. It is the bell curve. It's the normal curve. If you just take the coefficients from Pascal's triangle and graph them, they are the normal curve. even something like this, 1, 2, 1, right? 1, 2, 1, bell curve. So here's the binomial expansion all the way up to x plus y to the 7th. And you can see those same numbers, right? They're all in red here. 1, 1, 1, 2, 1, 1, 3, 3, 1, all the way down. How many terms are there in the last line, which is x plus y to the 7th? How many should there be? There should be 8, right? 1, 2, 3, 4, 5, 6, 7, 8. So you know, because these are symmetric, that if there's an even number of terms, the two in the middle have to have the same coefficient, right? If it's an odd number of terms, the one in the middle is unique, but then the two on either side are the same because they're symmetric. So this gives us a way for us to generate these binomial coefficients. So we need to know that, and then we need to know the pattern of the variables, right? So that's all there is really to this. So here's expanding a binomial. Expanding x plus 1 to the 3rd power. So since it's x plus 1 to the 3rd power, how many terms are there? 4, right? There's one, because this is n equals 3, therefore 4 terms. Right? The first term will be all x, right? The next term will be x squared y to the 1st. That's wrong, isn't it? We don't have a y. We have a 1 times 1. The next term, and I'm leaving a space because I know I'm going to fill in some coefficients later. The next term will be x to the 1st times 1 squared. And the last term will be 1 to the 3rd. Now, obviously, I could just go backwards to that slide and get the coefficients, but you won't always be able to do that. Usually, just go ahead and make yourself a triangle until you get down to that row, which has got 4 coefficients, and then you stick them in, right? So 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, right? Just adding up the numbers to the on top, to the left and to the right. So there's my 4 coefficients. 1, 3, 3, and 1. I won't even write it in there. And now I can simplify that, right? I don't need to write 1 times anything. I just say x to the 3rd plus 3x squared plus 3x plus 1. That's a bad raised to the 3rd power. Good. Okay, do another one. Now, I'm doing just like, there's going to be this one and then one more, and then that's it. All right. What's different about this one than the one before is now that second term is negative. So that's gonna make it look just a little bit different. Okay, so first of all, this one we're going to the 4th power. How many terms will we have? 5 terms. So how many coefficients do I need from Pascal's triangle? 5. Okay. The first term will be, right, notice that in our pattern, the first term here is if I was doing this like an x plus y or an a plus b, the first one is 2x, right? So that's got to be 2x raised to the fourth. The next term is going to have 2x raised to the third, and now it'll have negative 3 raised to the first. Right? Probably should have written that smaller, but the next term will have 2x squared and have negative 3 squared. Right? The next term will have 2x to the first and negative 3 to the third. And the next one will be negative 3 to the fourth. Notice that in every term, if you add up the exponents, they add up to the n, right? The n is 4. So 4, 3 and 1 is 4, 2 and 2 is 4. Every term, it's got to be exactly equal to that. Now, I need the coefficients. I need 5 coefficients because I got 5 terms. So 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. I need one more. 1, 4, 6, 4, 1. I mean, you don't always have to start at the top row. If you actually know one of the rows, like 1, 3, 3, 1, okay, just start there. That's fine. And so I need 1, 4, 6, 4, 1. And then you got to simplify, right? There's in each one where you raise 2x to the power, right? That's going to be 2 raised to a power and the x raised to a power. Right, so this first term, 2 to the fourth is 16. 2 times 2 times 2 times 2. So the first term is 16x to the fourth. Right. Now, the next term has got 4 times 2 to the third. This is 4 times 2 to the third times negative 3. What is 2 to the third? 8. So this 4 times 2 to the third is 4 times 8 is 32. 32 times negative 3. How about minus 96? You could check me, I could be wrong. And then you still got the x to the third. Right, the next term is going to be x squared, but I got to figure out the coefficient, right? The coefficient is not just the number from Pascal's triangle. We got to take care of the other things too. Right, so this is 6 times 2 squared times negative 3 squared. Which again, you could plug in, that's 6 times 4 times 9. 4 times 9 is 36. 4 times 36 is 144. So this is plus 144x squared. Right, the next is 4 times 2 times negative 3 to the third. Well, let's see. 4 times 2 is 8. 8 times negative 27. Is that negative 207? Negative 216? Negative 216. Minus 216, and we're still x in that term. And then the last, the negative 3 to the fourth is plus 81. So notice, because that second term was negative, your terms have to alternate sign. Right? Because as you raise a negative number to powers, you know, to an even power it's positive, to an odd power it's negative. Even, odd, even. So plus, minus, plus, minus, plus. So it's kind of 3 steps here, right? First, got to know how many terms you need. Write down those terms in terms of the what's being raised to what power. Then add your binomial coefficients, Pascal's triangle. Then simplify. Yeah. Yes. Always one more. So one more, and that is, now what's different about this one? Actually, one of the terms of the binomial is squared itself. So that's going to change the pattern of the powers, right? So let's see, this one is to the third power. So how many terms do we have? 4 terms. So the first term will be all the x squared term, this time raised to the third power. Right. The next term will be that x squared term raised to the second power, and now it'll be 4 to the first power. The next term will be x squared raised to the first power, and 4 squared. And the last term will be no x squared, it'll be 4 to the third. And now we need how many coefficients? 4, right? And, we've already been that far in Pascal's triangle, like every problem that we've done, that's 1, 3, 3, 1. So we put in a 1, and a 3, and a 3, and a 1. And simplify. Right, this first term, what is x squared to the third power? What do you do with exponents when you raise a power to a power? Try again. You multiply them. Right, so that is x to the 6th. Okay, the next one is going to be 3 times x squared squared times 4. So the 3 times 4 part is 12, and x squared squared is 4. Right, the next one will be 3 times 4 squared, 3 times 16, 48. And now it's just x squared once. And the last one, 1 times 4 to the third. 4 to the third is 64. So that's binomial expansion. What's that? That's a multiply. Right? Okay. So essentially, we just learned how to make a sequence of numbers. It wasn't arithmetic. It wasn't geometric. It had a purpose here. Like I said, it's actually pretty important because it is the normal curve. So those numbers are actually the normal curve. What is the normal curve? Normal curve is, if you do a distribution of random processes, it's the foundation of all statistics, most of the statistics we do in this country. Okay. So not much homework, right? It's the first couple are just, do the combination thing a couple times. And then the next 3 are do a binomial expansion. And it should be one that's like our first example, one was like our second example, one was like our third example. That's it.